Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is to draw the Lewis structure of pH3. So this is phosphine. And when we want to draw out Lewis structures, the first thing I want to do is to find the total number of valence electrons in the molecule. So for pH3, we have phosphine, or phosphorus, which has 5 valence electrons. And we have hydrogen, which has 1 valence electron, and 3 hydrogen atoms in total. So we have 8 valence electrons in pH3. So now I want to draw out my central atom, which is the phosphorus. And all around it, I'm going to draw out the terminal atoms, which are the hydrogens. So I'm just going to draw a single bond to all of the hydrogens. And now hydrogen is content because it only has that 1 electron to share. It doesn't need any more lone pairs. And for our total valence electrons, we need 8. And so far I've drawn 6, and this is because each bond contains 2 electrons being shared. So now I just need 2 more electrons and they'll be lone pairs on my phosphorus. And now this is the final Lewis structure of pH3. Okay, so now let's see what the junior tutor said. The Lewis structure of phosphine, pH3, is 3 hydrogen atoms bonded to a phosphorus atom, which is in the center, with a lone pair of electrons on top of the phosphorus atom. The Lewis dot structure represents the arrangement of electrons, shown as dots, between atoms in a molecule. The atoms must follow the octet rule or the tendency of atoms to prefer to have 8 electrons in the valence shell. The individual formal charge of each atom, as well as the overall formal charge of the molecule, must be satisfied. In the drawing, the electron dot structure, they mean phosphine, of pH3. Step 1 is to draw the skeletal structure of pH3 with phosphorus at the center. Okay, so step 2 is when they calculated their total valence of electrons. I usually do that first, but it doesn't really matter. And here they have 5 plus 3, which is equal to 8. Step 3 is to distribute the electrons as dots. Note the octet rule must be satisfied for phosphorus atom. However, hydrogen can only share 2 electrons. Step 4, replace the 2 electrons with a single bond between phosphorus and hydrogen, and then a lone pair of electrons will be left at the top of the central phosphorus atom. Yep, so this solution is correct. Okay, so on to question number 2. What is the molar mass of silver nitrate, which is silver AgNO3 in grams per mole? And then they give us a whole bunch of different options. So to calculate the molar mass of silver nitrate, we would need all the different atomic masses of the elements involved in the compound. And to do this, you would just find them on your periodic table, labeled as atomic mass or molar mass. But to find the molar mass of silver nitrate, it would just be the molar mass of silver plus the molar mass of nitrogen plus 3 times the molar mass of oxygen. So for silver, its atomic mass is 107.87 grams per mole plus the molar mass of nitrogen, which is 14.01 grams per mole. And then finally, 3 times the molar mass of oxygen, which is around 16 grams per mole. Okay, so if we add up all the different values, we end up getting a total molar mass of 169.9 grams per mole. So let's look at all the options. And so this is option D in the question. So 170. And see what the junior tutor said. The molar mass of a compound is the sum of the individual atomic masses of the elements comprising the compound. And they also got around 169.9, and the answer is D. Yep, so this solution is correct. Okay, so question number 3. What is another name for a condensation reaction? Okay, so I'll briefly just describe what a condensation reaction is. This is when two small combine. Okay, so a condensation is when two small molecules can combine to form a larger molecule plus water as a byproduct. So another word for condensation reaction is a dehydration reaction. So option D. Okay, so let me just draw out an example showing two amino acids. So every amino acid contains an amine group, which is NH3. And let me just draw out. They contain a carboxylic acid functionality as well, and a hydrogen And what makes every amino acid unique is that they have a different R group. So this can be any of the main groups. So like if it was an H, it would be like glycine, phenylalanine. So depending on the R group, you get a totally different amino acid. Okay, so let's say this was combined with another amino acid. So we have another amine group with a different R group. So I'll just denote it as R prime. And again, it still has the carboxylic acid functionality. But during a condensation reaction, the two amino acids kind of like combine. And you can see where water can be formed as a byproduct. And our final product is the combination of the two to get a larger peptide. Okay, so let's see what the junior tutor said. Condensation reaction pertains to a type of reaction that produces a small molecule, usually water, as a result of the combination of two reactants. An example reaction is shown below. The reaction above, since the reactants lost a water molecule, this condensation reaction can be referred to as a dehydration reaction. Therefore, the answer is D. Yep, so this solution is correct. Okay, so question number 4 asks to draw the Lewis structure for arsenic pentafluoride. Okay, so when we draw Lewis structures, I first want to find out my total number of valence electrons in the molecule. In the case of arsenic, it has 5 valence electrons. And in the case of fluorine, there are 7 valence electrons. So our molecule is arsenic pentafluoride. So I need to multiply this by 5. And then, so 35 plus 5 is 40 valence electrons in total. Now it sounds like a lot, but once you actually draw it, so let's draw arsenic in the middle as our central atom. And then all of the fluorine atoms around it. Try to make it symmetric. And each has a single bond to arsenic. So each bond contains 2 electrons. So far I've drawn 10 electrons out of the 40. So now I'm just going to draw all the lone pairs on my fluorine atoms. So each fluorine has 3 lone pairs, or 6 in total. Okay, so now I have drawn out all the lone pairs on my fluorines. And now let's see if we have 40 electrons drawn in the structure. So again, each bond contains 2 electrons, so I count out 5 bonds, so that's 10. So I need 30 more, but each fluorine contains 6 electrons that are in the form of valence pairs. And there are 5, so 6 times 5 is 30. So I have reached my 40 electron count, and I don't need to draw anymore. So this is the final Lewis structure for arsenic pentafluoride. And the junior tutor said to first determine the total number of valence electrons. The arsenic atom in group 15 has 5 valence electrons, and the fluorine atoms in group 17 have 7 electrons each. Total number of valence electrons is 40. Second, write a plausible skeletal structure by joining atoms through single covalent bonds. Okay. And then third, subtract 2 electrons for each bond in the skeletal structure. The 5 bonds in this structure account for 10 of the 40 valence electrons. This leaves 30 valence electrons to be assigned. So lastly, complete octets for the terminal fluorine atoms. Yep. So great step-by-step answer. So this solution is correct. Okay, so question number 5 is to draw the major product formed in the following reaction. So we start off with this epoxy or epoxide ring that has an ethyl group, and it reacts with sodium cyanide, ethanol, so I'll just write ETOH, and water. Okay, so let's analyze what we have given for this reaction. We have this epoxide ring, which are generally pretty strained and are easy to break, so that's one thing to note. And we have sodium cyanide, which is a strong base and is good to act as a nucleophile. Okay, so if we are to draw out the mechanism that occurs for this reaction, we have the cyanide ion coming in to open up the ring on the least sterically hindered side. So this gives us the following intermediate, where we have our cyanide ion. We have the ring that is now opened up, and then we just have our ethyl group that remains the same. So now we have this negatively charged oxygen. This is when the water molecule is involved, because this negatively charged oxygen will get protonated to give us our final product, which now has a new cyanide group, an alcohol group, and the remaining ethyl as our final product. So if we were to name this molecule, we first need to number it. So starting from the cyanide is carbon 1, 2, 3, 4, 5. We have a 5 carbon long chain. So pent will be our parent name, And then on carbon 3 is an alcohol group. So to signify that, oh, you guys can't even see the final structure. Hold on, let me move this down a bit. Okay, so we have the cyanide group. And an alcohol group. Yep, so this is our final product that you can now see. And again, I'm going to number carbon 1, 2, 3, 4, and 5. And on carbon 3 is an alcohol group, so we're going to signify it as 3-hydroxy. And the reason for this is because the main carbon that we're looking at is the nitrile, so this will be our suffix. It is more prioritized than the alcohol group in terms of functional groups. So 3-hydroxy, and then our parent name was penta. And our suffix is just nitrile, so pentane nitrile. Okay, so I'll also write down what happened in this mechanism, which is referred to as an SN2 mechanism. So the epoxide ring opened up, and the cyanide ion then attacks the less hindered carbon. Okay, so now let's see what the junior tutor said. A nucleophilic ring opening occurs when epoxides are treated with nucleophilic reagents. Base-catalyzed epoxide opening is a typical SN2 reaction in which the attack of the nucleophile takes place at the less hindered epoxide carbon. Make a new bond between the nucleophile and an electrophile and simultaneously break a bond to give a stable molecule. Backside attack of the nucleophile on the less hindered carbon of the highly strained epoxide opens the ring and displaces O-. Or displaces O-. So yeah, and they have 3-hydroxy pentane nitrile. Okay, so this solution is correct. Okay, so question number 6 is to draw the neutral organic products. So we start off with a cyclohexane and a bromine group on it. And all it reacts with is H2O. So water is considered a weak nucleophile. And now let's analyze our reactant. we have a secondary alkyl halide. And a poor nucleophile. So this tells us that the reaction can proceed through two different mechanisms. So one is the SN1 mechanism, or an elimination reaction, so E1 mechanisms. If we had a substitution reaction, then it would give us the following product, where the bromine group is substituted with an alcohol. So this is the substitution product. And for the elimination reaction, we have our ring. And instead of being replaced with an alcohol, the bromine is just a leaving group, and a double bond is formed and it's placed. So this would be the elimination product. So the junior tutor said that nucleophilic substitution is any reaction in which a nucleophile replaces another electron-rich group called a leaving group. A nucleophile is an electron-rich molecule or ion that donates a pair of electrons to another atom or ion to form a new covalent bond. Yep, so the junior tutor drew the example of the nucleophilic substitution reaction. So I'm going to say that this solution is correct. But also, since water is a weak nucleophile, this reaction can proceed through both SN1 or E1 mechanisms. Okay, so I said that in the case of the elimination reaction, cyclohexene is formed. Okay, so question number 7. What is the relationship between the following two compounds? Let me draw out both of them. Sorry, that was a poorly drawn ring. So notice that we have two things going on. We have different, like an inversion going on with the hydrogen and the methyl group. And the double bond is also in a different place as well. So I'm going to say that out of all the options given, these can be constitutional isomers. So constitutional isomers is when we have the same molecular formula, but different connectivity. Okay, so the junior tutor said that the following compounds are constitutional isomers because they have the same molecular formula, but the substituents are in different positions. Okay, so this solution is correct. Okay, so question number 8. Which is the major product for the following reaction? So they have an aminobenzene, that reacts with nitric acid, HNO2, 0 to 5 degrees Celsius, and another aromatic group, and sodium hydroxide. Okay, so now let's analyze what we have. We have a primary aromatic amine, and it reacts with nitrous acid. So it reacts with nitric acid, or nitrous acid, sorry. Since it's HNO2 instead of 3, we have nitrous acid and the name of this reaction is the formation of arene diazonium salts. So the following product, we have our first benzene group, nitrogen, that is double bonded with another nitrogen. So this nitrogen is from the nitrous acid. And then our second benzene ring that has the alcohol and a methyl group in the para position. So now let's see all the different options that they give us. So the following product would then be compound number 5. I should also draw it in Roman numerals, compound V. And the junior tutor said that primary aromatic amines react with nitrous acid to form arene diazonium salts, which, unlike their aliphatic counterparts, are stable at 0 degrees Celsius and can be kept in solution for short periods without decomposition. When an arene diazonium salt is treated with an appropriate reagent, nitrogen is lost and replaced with another atom or functional group. Arene diazonium salts undergo a coupling reaction with activated aromatic rings, such as phenols and aryl amines, to yield a brightly colored azo compound. And then they show your aromatic with the nitrogen double bonded with another nitrogen and aromatic ring. Okay, so this solution is correct. Okay, so question number 9 just asks, what is a Lewis acid? So we have a Lewis acid, which is an electron pair acceptor. And let's compare this with a Lewis base. Which, as you can guess, is the opposite of a Lewis acid. And it is an electron pair donor. Now let's have an example for the two. In the case of a Lewis acid, an example of this would be like NH3. So this ammonia ion has a lone pair that is capable of donating its electrons. So therefore, this is a Lewis acid. And an example of a Lewis base. Oh, sorry, I got the 2 mixed up. That makes sense, sorry. So the Lewis base is the NH3 because it can donate electron pairs through its lone pair. So NH3, I got the two mixed up in my notes as well. The lone pair that can donate electrons. Put this in a box. But the Lewis acid, on the other hand, since it accepts electrons, an example of one is boron trichloride. And this molecule has an empty orbital. Well, boron has an empty orbital. Therefore, this is a Lewis acid. Okay, so sorry about that fusion, but we can also compare this with Bronsted acids and bases. So if you're wondering why these ones have a different name, Bronsted. So a Bronsted acid is defined as a proton donor. And a Bronsted base is a proton acceptor. Okay, so the reason why you can have a Lewis acid that isn't a Bronsted acid is because sometimes it doesn't have a hydrogen to donate. Like in the case of boron trichloride, there are no hydrogens, so this can't be a Bronsted acid since Bronsted acids are proton donors. So an example would be like HCl or even water. And an example of a Bronsted base, you could also have NH3, which can accept another proton and become NH4+. And even water again can act as both a Bronsted acid and a Bronsted base. So the junior tutor said that by definition, a Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. For example, let us consider the reaction below. We have mercury 2 plus 4 cyanide ions makes mercury cyanide. And from the given reaction, mercury 2 plus is positively charged. Thus, it is most likely to accept electrons rather than lose electrons. In this case, the mercury acts as Lewis acid. Okay, so this solution is correct. Okay, so question number 10. Which of the following best explains why electrolytes solutions conduct electricity? A, the presence of water, B, the presence of free-flowing electrons, C, the presence of free-flowing ions, or D, the presence of atoms. Okay, so first I'll just give a brief definition for electrolytes. So electrolytes in general, they dissociate into ions when dissolved in water. And this is how they conduct electricity. So when we have a strong electrolyte, this means that it fully dissociates into its ions when dissolved in water. You can have a weak electrolyte, which means that it only partially dissociates into its ions. And you can have a non-electrolyte, where it doesn't dissociate into its ions at all. So since we know the definition of electrolytes, we can just say that they conduct electricity due to the presence of free-flowing ions. So ions are just an atom that has a charge. So it can be negatively charged, an anion, or positively charged, which is a cation. So the Janine The Tutor said that when voltage is applied on an electrolyte, a negative charge on the cathode and positive charge in the anode is produced. Ions neutralize these charges, and it enables electrons to keep flowing. Electron current is defined as the flow of electrons. This is why electrolyte solution conducts electricity due to the free-flowing electrons. Okay, so it's true that we need free-flowing electrons in order to conduct electricity, but the point of an electrolyte solution, again, is because they are able to dissociate into their ions, which is also needed to conduct electricity. So the solution okay, first I'll just say that electrolytes okay, so I said that electrolytes dissociate into ions when dissolved in water and conduct electricity. Therefore, the correct option is C, the presence of free-flowing ions. Electrons are also needed to conduct electricity, but C best explains why electrolytes solutions conduct electricity. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, go ahead and give it a thumbs up and a comment, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.